But today we're gonna do a couple of problems that are challenging. Number 13 on that homework, I think, is one of the ones that you mentioned, or somebody mentioned that. Just a reminder, so I believe we had this reaction that we were looking at, trying to understand the idea that we cannot create, we cannot destroy matter, we can only transform it. And we had this compound becoming these two compounds, or these two molecules rather. You remember that?
Yes.
That's what we had on Tuesday. And we went beyond and described this as a chemical reaction known as a decomposition. If I didn't mention that, I want to mention it today because we're going to talk about at least one other type of chemical reaction, maybe even more, but at the very least one. So decomposition means a somewhat larger molecule becomes two somewhat smaller molecules. And the somewhat is, this doesn't look much bigger than those two, but if you look at it carefully, this has one more oxygen per unit than this guy. So it is slightly bigger. And that comes out from what is going to happen to this oxygen. We did more. We labeled these as the states of matter, how they appear in nature. This is always a liquid, so we mark that with a lowercase l. And the water that comes out of that reaction was also labeled as a liquid. Water is kind of interesting because in one of the reactions that we're going to look at today, it's not going to be a liquid, it's going to be a gas. It's going to be steam or vapor. But in this particular case, it's a liquid. And oxygen, almost all the time, unless you do this at a very cold temperature, is going to be a gas. And if you remember also, we said this is hydrogen peroxide, the stuff that we all have, or most of us have in our medicine cabinet. If you put hydrogen peroxide on an open wound, it fizzles. That bubbling is this oxygen being produced. And of course, that reaction, as written here, does take place. It's happening all the time in that bottle. You don't see it. You don't see when you open hydrogen peroxide and look inside the bottle bubbling because the reaction is very slow. It's taking place in slow motion. When it bubbles after adding it to an open wound or to something that is dirty, is because there's an enzyme there. Enzymes are not part of this course, but enzymes are molecules that make these reactions go really fast. So that enzyme makes this reaction proceed at a speed that you can actually see the oxygen bubbling. But under normal conditions in your medicine cabinet, this is happening very slowly. It's still nevertheless happening. Now, we also said last time that these are the right formulas for these three chemicals, but they are not the right amounts. For this reaction to proceed, you need to put the amounts of ingredients, the amount of the chemicals in the right proportions without changing the formulas. These have to remain just as they are. And we ended up with a big 2 in front of these, and I believe we had a big 2 in front of that, and that was it. So if you review your notes, you may see that this is what we call a balanced chemical equation. We did that part to make sure that we have the right amount of everything without any excess, without any what should I call them? Ingredients missing, if you will. So we have enough of this, enough of that to have it balanced. How did we discover that? Do you guys remember? We added every single atom on both sides of the arrow. So this arrow tells you that there's a transformation going on. There is a stuff before the arrow, which we call the reactants. And we have the stuff after the arrow, which we call the products, or chemists call the products. Sometimes there's more than one product, sometimes there's more than one reactant. In this case, there's only one. Finally, what we did is we did some accounting. We counted the hydrogen on the left side of the reaction, on the reactant side. We said there's 2 times 2, 4 hydrogens. And we also said there were 2 times 2, 4 oxygens total on this side. On the right side, there were 2 times 2, 4 hydrogens. And then 2 times 1 is 2 oxygens plus this other oxygen that is here, which is also 2, to give you 4 oxygens. So these numbers are the same before and after, telling us that this is a balanced equation. If they were not, then we would have to fix it. And when we fix it, we only add numbers that are in front of the formulas. We don't change the formulas. So that's a quick review of what we did. Today we're going to look at a problem that at first looks a little scary. I mean, I have to admit, when I look at this problem every time, it's like, oh my God, how are we going to solve this problem? It looks so complicated. But it really isn't. And I want to start by showing you the simplest example of what we're going to call combustion. Let me just enter my password here. I hope I got it right. So any questions about this? Because I'm going to erase it. Now, remember, this is a chemical reaction of a kind known as a decomposition. Now we're going to write another type of chemical reaction that in general is called combustion. So this is called a combustion reaction. Now you may have heard that term in plain English, but if you haven't, it just means burning. You know, when you burn wood on a fire, you are performing a combustion reaction. When you burn gas on a stove, you are conducting a combustion. So that's just a chemical name for that. Now, all combustions have something in common. They all need oxygen. Without oxygen, things cannot burn. And all combustions produce carbon dioxide, and they also produce water. There are other reactions that can be classified as combustion in which there's going to be other products, but this is the generic one. This is the one that we need to understand first and foremost. Now, I'm missing here the key ingredient. So this is what we're going to burn. That's the fuel, okay? Now, there's many different kinds of fuel, many different things that you can burn. I mean, we could burn this desk, and that would be the fuel. I don't know the formula, the chemical formula for this desk, so I'm not going to bother with that. But I do know the chemical formula of a very simple compound called a hydrocarbon. So this is a generic name for compounds that have only hydrogen and carbon as their ingredients. So hydrocarbons only have carbon and hydrogen, nothing else. The simplest of all, and we're going to start with that, is something called methane. And it has this chemical formula. 1 carbon, 4 hydrogens. And that's it. So it's a simple chemical. Now, let's review a little bit of what we learned in chapter 6, I think. This molecule, if I were to show you all of the electrons here, would actually look like this. Same thing, except that here I'm showing you where each hydrogen is interacting with the carbon. So each hydrogen is bringing 1 electron. That 1 electron is being shared with the carbon. The carbon shares also 1 electron. Remember from chapter 6, every dash, when we draw things like this, represents 1 pair of electrons, the so-called bonding pair of electrons. Why am I showing you that? Well, because we're going to look at other examples beyond this, and I want you to see how they get bigger and bigger as we add more carbon to different compounds. But this guy is called methane. I'm underlining the ending because we're going to look at some other examples that have the same ending on the name. Now, let's start with this very first combustion, and I'm going to tell you that these are the right formulas for the chemicals that we're going to analyze. So we're going to burn methane in the presence of oxygen to produce carbon dioxide and water with the proper formulas. I'm going to start adding some symbols that you've never seen before, at least one symbol. The ones that you've seen before are, well, the state of matter of methane. Methane is a gas at room temperature. So that's a gas. This guy is always a gas. Carbon dioxide at room temperature is also a gas. And water, as you saw before, can be a liquid, but in this case it's going to be a gas because we're burning something. So it's actually too hot for water to be liquid. It's going to be boiling, so it's going to be a gas. The one symbol that we haven't seen before, I'm going to put it on top of the arrow. I don't think it's needed in your homework problem, but I'm going to add it here so that you see it. And it's a triangle. That triangle means heat. You have to heat this up in order to burn it. You need to get it going. Okay, now, let's go back. I'm going to erase the name on this because I need the space. And look at the number of chemicals and the amount of every chemical and see if this is balanced. Remember, we're not God. We cannot create matter. We cannot destroy matter. We can only transform it. So methane, oxygen, CO2, and water are already given to us. But what we can do is decide the right amounts that we need of these. We cannot create methane, but we can say, okay, we have 1 methane, 2 methanes, 50 methanes. It doesn't matter. The chemical equation is the recipe for making those products from these ingredients. So how much of these do we need with how much of that to produce how much of this and how much of that? Well, that is based on the number of every atom on both sides of the equation. So let's do the accounting. And with your help, how many carbons do you see on the left side of the arrow, on this side? 1 carbon. So we have 1 carbon here. And let's pay attention only to carbon for now. Let's go to the other side and see how many we see on the other side. 1 carbon also. So the amount of carbon is fine. We don't need to touch the carbons yet. We'll see what happens next. Now let's take a look at the next element. The next element is hydrogen, and how many do we have on the left side? So that 4 belongs to the hydrogen, which tells me I actually have 4 hydrogens in one of these CH4s. Remember, we're going to start calling them moles. when I say atoms, I really mean to say moles. We introduced the term mole last time as an amount like a dozen, but it's much bigger. So this is 1 mole of carbon in 1 mole of methane, and these are 4 moles of hydrogen in 1 mole of methane. Okay, so how many hydrogens on the right? We're looking only at hydrogen, H2. So we have H and a 2, grand total? 2 hydrogens. There's no hydrogen here. There's only a 2 there belonging to this H. If I show you this with bonds, it looks like that. So there's 1 and 2 hydrogens. That's it. Okay? Well, we have a problem because we have more hydrogen on this side than what we are saying is being produced. We have to fix that. We cannot fix that by changing the formula. CH4 has to stay CH4. In other words, I cannot say, well, I have 4, I'm just going to say CH2. That's wrong. It's wrong because this is a different chemical. It does exist, but it's not methane, and we cannot change the formula. We can only do the following. What we did with the hydrogen peroxide, with the previous example, and that is put numbers. Let me put a box in a different color here. I think I have a different color. We can only add what are known as coefficients. We can put a number in front of the chemical formulas of everything involved here. When we do that, all we are saying is we have, remember also, please, everyone, that when we don't write anything, there's an implied 1. That we don't write it because it's implied. So there's a 1 there, there's a 1 there, there's a 1 there, and there is a 1 there. But we're not going to write them because chemists try to simplify things. Now, there's nothing wrong with me adding a different number than 1. I can put a 2 here. And what that is saying may not be correct, but what that is saying is that for every 2 of these, I need 1 of that to produce 1 of that and 1 of that. When I do the accounting, I have 2 carbons, 8 hydrogens, and over here I have 1 carbon and 2 hydrogens. So that didn't help. That made it worse. In my example from last time of making pancakes.
I'm sorry.
Yes.
Really quick question.
Yes.
For my own sake. So in order for us to get to here, we have to do this on paper first.
Yes, sir.
Before we actually mix the chemicals.
Absolutely.
To achieve the...
Absolutely, to count, yes, yes. So if you're going to set up this experiment for real in the lab, you need to figure it out on a piece of paper how much you need of each. Now, later in the semester, well, you're not going to be here, but that's okay because you're going to be somewhere watching what we did or doing the homework. There's nothing wrong with doing this with more of this than what we need. What is going to happen is if I have more of these of what we need and we have just enough of these, we're going to have leftovers. So if you're making pancakes at home and you follow the recipe that I gave you, you need 1 egg, 1 cup of flour, 1 cup of milk to make pancakes. If you want to make twice as many pancakes, you use 2 eggs, 2 cups of milk, 2 cups of flour. If you want to make the half amount of pancakes, you use, well, you can use half an egg, half a cup, and half a cup of flour, half a cup of milk. But if you have 5 eggs and only 1 cup of flour and only 1 cup of milk, well, you're going to make only enough pancakes with 1 egg, and you're going to have 4 eggs left over. So there's nothing wrong with having leftovers. These numbers are going to work to tell you whether or not you have leftovers. The idea right now is to not have any leftovers, to have just the right amounts so that everything is balanced. That's where we start.
I have a question.
Yes.
So on that side, there was 4 hydrogens, on that side, there was 2. So wouldn't that be 6? I'm trying to figure out how you got the 8 hydrogens.
Well, the 8 hydrogens I got them by an example that is not going to work. These two,
So not to remember.
let me erase it and show it to you. These two basically is saying in this imaginary experiment that we have one of those and then 2, the second one of those. So you have 2 of that, which is 1 and 2. If we count hydrogens here, you have 1, 2, 3, 4, 5, 6, 7, 8. Now that doesn't work though, because what I'm trying to achieve, Joan, is the following. Let's go back and put the original accounting. I'm going to erase the 2. And I'm going to put the original accounting. It was 1 carbon, 4 hydrogens. In one of these guys, there's 1 carbon, 4 hydrogens. That's it. The goal right now is to make sure that we have somehow 4 hydrogens on this side and 4 hydrogens on that side. That's what we're trying to achieve. Now, there's a way of doing that. Please be mindful of the following. This procedure is known as trial and error. You're going to try numbers, and then you're going to see what happens. With practice, this is going to become less of a trial and less of an error. But the very first time, we don't know. I just make a mistake, an error. I put a 2 there. That didn't help. Well, let me skip to what I know is going to work, and I'm going to put a 2 here. I'm trying that. Let's see if that gives me the right answer or not. If we do the accounting again, we haven't changed this, so this is 1 carbon still, right? And there are still 4 hydrogens here. We haven't changed that. But if we come to this side, now we do the accounting. For hydrogen only, we have 2 times 2, 4 hydrogens. We didn't touch the carbon, so we still have 1 carbon, right? So the carbon is balanced because it has the same amount. The hydrogen is balanced because we added that 2, and that made this a 4 hydrogen total. So we are on the way to balancing this equation, to fixing it, to having the right amount of ingredients. We're not done because now we have to count oxygens. How many oxygens do we have? Well, there's a 1 here that we don't write. 1 times 2 is 2, so there are 2 oxygens. And on this side, we have 1 times 2, 2 oxygens. But we also have oxygen in the water. 2 times 1 is also 2. It's not only 1, because we have 2 of these. So we have HOH and HOH, 1 and 2 oxygens. So don't forget, this number in front of the molecule, which we call a coefficient, oops, I'm missing the E, affects the whole molecule, not only the first element. So that too makes these 4 hydrogens and 2 oxygens. So that means we have a total of 4 oxygens, and we only have 2 over here. So we're not done. We need to keep trying. Well, what else can we do? We don't want to touch this because it's already fixed. But this is by itself. The oxygen is not combined with anything else. So what happens if I try the following? I put a 2 here. All of a sudden, by just putting a 2 there and saying I have 2 oxygen molecules combining with 1 methane molecule, that gives me 2 times 2, 4 oxygens. And then if I go back and look at everything, this equation with those 2 additions, the 2 numbers that I added, is balanced. Now I can erase the boxes so that you see the final product of our effort to fix the amount of ingredients, to fix the recipe, if you will. And what we say at the end of the process is the following, and this is important. We are saying that to burn methane, you need 1 mole of methane for every 2 moles of oxygen, which are going to produce 1 mole of carbon dioxide and 2 moles of water. And that's exact. Now, yes?
So what you do to one side, you do on the other side?
Yes. You have to do one side with the other side always. You need to make sure that they have the same amount on both sides. Absolutely. Now,
But you can add a coefficient to only one side, right?
you can add a coefficient anywhere, but only to the left.
If I add a coefficient over here, I don't have to do anything over there. All I'm trying to do is balance.
That's right. Right, by trial and error. But if I put a coefficient, let's say that I made a mistake and instead of putting a 2 there, I put a 2 here. There's nothing wrong with that except that it's not balanced because now you have 2 carbons here, only 1 carbon there. We need to always find the right amount, the Goldilocks amount, if you will, the perfect amount on both sides of the...
So what happens if you have an odd number?
Very good question. And we're going to do that with the problem. You can encounter that, and we're going to encounter that. So, yes, indeed, you can have an odd number, but you cannot have fractions. You cannot have 2.5, 2.3, 1.9. They have to be whole numbers. They certainly can be odd, but only if that's what it works. Now,
instead of it being 02, what if it somehow was like 03
well,
or 05?
there's nothing wrong. We just balance it. We just do the arithmetic. Now, check this out. There's nothing wrong with me doing the following. As long, I'm glad you asked that question, Jerry, because this is going to give me the opportunity to change this simply by saying, okay, so this equation is now balanced. It means 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of CO2 and 2 moles of water. Okay? Now, what if I want to make a lot of these? What if I don't want to make only, or what if I want to burn more methane than 1 mole? Well, I can change the amount. But if I change the amount and I want this to be balanced, not have anything left over, not need anything more, I have to do whatever I'm going to do right now to everything. So let's say that instead of burning 1 mole of propane, I want to burn 5 moles of propane. So I'm going to put a 5 here. I need to multiply everything by 5 to keep it balanced. So 5 times 2 is 10. 5 times 1 is 5. 5 times 2 is 10. And if we add everything again, it's still going to be balanced because we did not alter the proportions. If I make this 50, then this is 100, that's 50, that's 100. The proportions. Now, that doesn't mean that you have to always do it precisely like this. If I make these 5 and I only have 5 of these, it's not balanced, but it's going to just not burn all of it. There's going to be left over. So we need to start somewhere, and we always start with the balanced equation. After that, we can do all kinds of predictions. But you need the balanced equation. Now, let's move on to a second example. It may be a little bit more challenging, but then we can move to the problem on the homework. So the second example is going to be another hydrocarbon. Remember, hydrocarbons are chemicals that have only hydrogen and carbon. And I'm going to leave methane there. I'm just going to show you the second one. The second hydrocarbon is going to look like this. Carbon, carbon, hydrogen, 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 and hydrogen. This is the second one that we're going to burn. So instead of having only 1 carbon, now it has 2. What is the formula for that? C2, 1, 2, 1, 2, 3, 4, 5, 6, H6. I'm going to erase this because I need the space. But that's what this one is. That's a real chemical, you guys. This one was called methane. This one is called ethane. Same ending. Hydrocarbon. It can be used as fuel. It does exist. It happens to be a gas. But there's nothing wrong with that. I can combine it with oxygen to produce carbon dioxide and water because it's a combustion. So when it burns, it produces the same products. And it needs the same oxygen as methane did. Except that now the accounting is different. Because now, if we start doing the accounting, we have 2 carbons, and we only have 1 carbon here. So right from the start, it's unbalanced based on the carbon. Trial and error. What can we add to the chemicals to balance the carbon? We're not looking at anything else right now. We put a 2 in front of the C, exactly. So now if we do the accounting for carbon and carbon only, we have still 2 carbons, and then 2 times 1, now we have 2 carbons. So good, we balance the carbon. Let's look at the hydrogen. We have 6 hydrogens here. 1 times 6 is 6. There's no hydrogen there, so that's it for the left side of the equation, for the reactant. How many hydrogens do we have here? I hope you see 2. 1 times 2, that's it. So that's not balanced. How do we make this side have 6 hydrogens? What can we do? Adding coefficients only. Yes?
2 times 3.
2 times 3. So a 3 here is going to make these 6. Absolutely. So 3 water molecules will contain 6 hydrogens. We now have 6 hydrogens. Very good. Wow, Jenna, you should come and be here more often. Okay, so 6 hydrogens and 6 hydrogens, balanced equation for the hydrogen and for the carbon. But we're not done. We have oxygen left there. So how many oxygens do we see here? Not 1. We see 1 mole of O2, but of atoms of O alone, we see 2, right? That is very easy to get confused by that. These always exist as bimolecular, but every one O2 has 2 O's. And on the right side, we have 2 times 2, 4, plus 3, 7. Yikes. I don't like that number because it's an odd number. So 2 times 2, 4. 3 times 1, 3. 4 plus 3, 7 oxygens. How on earth are we going to make these 2 be a 7? Well, that doesn't work, does it? Yes?
Can you like do 2 times 3 and then add 1? Can you do that?
If it adds up, yes. But if it doesn't, we need to fix it. So that's a good idea. That's a very good idea. Now, let me ask you this question. What is 7 divided by 2? 3.5, 3.5, right? So 3.5. Now, what do I mean by that? Well, okay, so a 3.5 number cannot be used in balancing these equations. In other words, if I were to put a 3.5 here, 3.52, that's why I did the divided by 2, is 7. And that will balance it, right? Trial and error. That doesn't work because we cannot use numbers that are not integer. However, and Jana, thanks to your contribution, I thought of that. So plus 3.5 is wrong, but it's not wrong because that gives you 7 oxygens, right? Now we have to do one trick to fix this so that chemists don't get mad. And that is change the 3.5 into a whole number. Well, we do the same thing that we did over here in reverse. We multiply that number by 2. So what is that multiplied by 2? 3.5 times 2 is 7. I'm going to put a 7 here. But because I multiply that by 2 and the equation was balanced, I have to multiply everything by 2. So I had to put a 2 there. 2 times 1 is 2. I have to multiply that by 2, so that's a 4. 2 times 2. I have to multiply this by 2, so 3 times 2 is 6. Let's take a look now. Let's count. So 2 times 2, 4 carbons, right? 4 times 1, 4 carbons. So carbon is balanced. 2 times 6 is not a trick question. You guys know how to do that arithmetic. 12, right? 2 times 6, 12 hydrogens. 6 times 2, 12, right? I'm not playing magical tricks here. I'm just adding. Finally, we have the oxygen left. 7 times 2, 14. And over here, 4 times 2, oh my God, it's not balanced. 8. And then 6 times 1, 6. 8 plus 6, 14. And it's balanced. It is crazy, but it's nothing other than patience, trial and error. If you had put another number, a random number, and it didn't work, you just keep trying. Now, what was the trick today? The trick was to say, okay, I cannot use fractions, but I can momentarily put a fractional number there and then fix it by treating the entire equation by multiplying by 2, in this case, the same. There's no simpler representation of this combustion. That's the only one that works. Okay, now, it gets, of course, more complicated than that. We're going to do one more, and then we'll look at the problem in the homework. The next hydrocarbon, so the first hydrocarbon was methane, has 1 carbon. The second hydrocarbon was called ethane, has 2 carbons. Well, you guessed it. The next one is going to be C3, 3 carbons, H8. How do I know? Well, I'll give you a clue soon. Let me just put the prediction of the generic combustion, and then we'll balance it. The hydrocarbons known as alkanes, you don't need to know this for the course. It's extra information. This ends in A and E. Methane, ethane, this one is called propane. Many of us use propane at home to burn, on our stoves. Fields Propane is one of the companies that supplies propane, at least to us. So that's propane right there. So if it ends on A and E, it's an alkane. And alkanes have the general formula like this. CN, where N can be any number, 1, 2, 3, 4, 5. H, N plus 2. Sorry, 2N plus 2. 2N plus 2, not only N. So if N is 3, H is 2 times 3, 6 plus 2, 8. If N is 4, H is 2 times 4, 8 plus 2, 10. If C is 5, H is going to be 2 times 5, 10 plus 2, 12. You see the progression? So this number is always double the carbon plus 2. Double plus 2, double plus 2. Those are all alkanes, and they exist. They are real. So this is propane, burning in oxygen, producing carbon dioxide and water. Now, let's do the accounting. We have 1 times 3, 3 carbons. I'm running out of ink. And on this side, only one carbon, right? How do we fix that? Trial and error. What can we try to make this side have 3? So we want 3 carbons on the right.
So do you just put 2?
If I put a 2 here, I have 2 times 1, I have 2 carbons, not 3. Okay, I mean, it's trial and error. That's perfectly fine. So that didn't work. What can we do? 3 CO2. 3 times 1, 3 carbons. This takes practice, you guys. Don't feel bad if you try and it's not the right number. You just keep trying. So now we have 3 carbons. 3 times 1, 3 carbons. So that's balanced. We accomplished something. Let's look at the hydrogen. How much hydrogen do we have here? 8 hydrogens. And on the right, 1 times 2, 2 hydrogens. So that's not balanced. What can we do to balance it? 2 times 4. 4 hydrogens, as Jerry said. Both of you are right. So 4 here will make these 4 times 2, 8. And now we have 8 and 8 without touching anything else. We only have the oxygen left. How many do we have on the left? 2 oxygens rather. And on the right, 3 times 2, 6, plus 4 times 1, 4. 4 plus 6, we have 10, right? 10 oxygens. Not balanced. How do we make this a 10?
2 times 6. Oh, wait, no. It's just...
You're on the right track. 2 times 6, no, but that's 12, so 2 times what?
Oh, 2 times 5, yeah.
5. There you go. A 5 there. We'll make that 5 times 2, 10. 10 oxygens. 4 times 1, 4. 3 times 2, 6. 6 plus 4, 10. Balanced. That's it. We're done. So you begin to see that if the number of carbons is odd, 1, 3, we don't have to mess with weird numbers. But if we do the next one, butane, we're going to have to deal with a fraction again. So let's leave that for the homework, because there's actually something called, nonane or octane, one of those. So we'll take a look at that next. Any questions about this? Because now we're going to look at the problem that looks scary at first, but it's not that bad. And you know what? You probably didn't even know this, but I was talking to students in a different class, and when I looked at the problem, it doesn't count. It's for practice only. So if you get it wrong, you don't lose any points. So, if you were spending like an hour trying to solve that problem, that's good for you because you are learning chemistry, but it doesn't affect your grade at all. It didn't have any credit. Okay, so I'm almost there. Let me just turn on the projector. Let's see. So this is chapter 7. And the homework. And we are dealing with problem. Is it up and running? Oh, finally. Oh, it looks like I already solved this one in my other class. But let's just do it from the beginning. So when you look at the problem, all of this is just a story that has nothing to do with the question. It's just telling you what is it that we are dealing with. It turns out that this imaginary case is about a woman who gets burned because an arson, because somebody actually started a fire. And they discovered through the investigation of trying to find out what was the cause of the fire that gasoline was used. So that somebody torched the place with gas. I mean, horrible, but it unfortunately happens. Now, the chemical investigators that are trying to address what happened are telling us that gasoline is a bunch of hydrocarbons. So gasoline has methane, ethane, propane, and these other guys. If you notice, only one doesn't end in A-N-E. So hexane, heptane, octane, nonane, decane. This one doesn't end in A-N-E. It's not an alkane, it's something called an alkene. It doesn't matter because we can look up the formula of toluene if that was the question. Now, the prefix here, not the suffix, but the prefix tells you how many carbons you have. On the three that we looked at, that prefix didn't help. Methane, I don't think it means one. Ethane, I don't think ethane means two. Propane certainly doesn't mean three. Butane doesn't. But beginning with 5, with pentane, penta means 5, hexa means 6, hepta 7, octa 8, nona 9, deca 10. So this has 6 carbons, 7 carbons, 8 carbons, 9, and 10 carbons. Toluene we're going to leave for last. Now that you know that alkanes have the generic formula, I can make this into hexane. The first question deals with nonane, okay? I already solved it, so let me see if I can do one that I didn't. It doesn't matter, we can do it, but, it looks like toluene is the one that I haven't solved. So we can do that. Before we do toluene, let's do decane, just for kicks. So decane means 10. The hydrocarbon that we're going to try to balance is now C10. The H is going to be 20 plus 2, 22. And let's try to balance that. And then we'll go back to toluene, and with that, we're going to wrap it up.
Liquid octane next, that's what I had.
Oh, liquid octane?
Yes.
Let's do octane then, instead of decane. Yeah, because we run out of time if I do both decane and octane. Yes?
Why can't we just say the regular number? Like, why do we have different?
Chemists are very special. I'll give you a very good reason. Because chemistry is worldwide, a worldwide effort. In other words, I come from Mexico. In Mexico, we do chemistry too. So imagine if I were to call 10ane for 10 or 9ane for 9, they wouldn't understand where they don't speak English. There, they would call it 10ane or 9ane, and it may sound like familiar. But when we use deca here, we use deca in Russia, we use deca in China, so it's to make it universal. That's the reason, no other reason. Yeah, you're right. And probably at one point in time when there was no communication with other countries, he was probably using those, 10ane for 10. But we... is based on, I think it's Latin. I think it's Latin, yes. So they are numbers in Latin. So let's do, John, you wanted 8ane? Octane, but 8ane. It's going to be octane. Okay, so C8, what is the value of hydrogen? 2 times 8, 16, plus 2, 18. That's the chemical formula for octane. So you need to have that. If you don't want to memorize this stuff, remember what you can use. You can use Wolfram Alpha. I mean, you can use the internet. Any Google website will probably help you with that, or any Googling it. But Wolfram Alpha is for chemists. So if I put here octane, just the word, it's gonna show me, I hope, the formula for octane. And is right, oops, come on. Right there. Can you see it, John? C8H18. So C8H18. You don't need to memorize them. Okay, so let's balance this one. I'm going to erase the other guys because it's too much information here. It's a little confusing. And let's look at only octane. So let's account for carbon. How many carbons on the left? 8 carbons. How many carbons on the right? Only 1, right? So how do we balance that? What number do we put in here so that we have a grand total of 8?
7. 1 times 8.
1 times 8. If we put a 7, we are imagining that we're adding that one. No, we only look at this, not at this. So 1 times 8 is 8. So 8 carbons. You're going to have to tutor your mom. No, just kidding. No, never mind. No, John, ignore that comment. Okay. So now we have 8 carbons and 8 carbons. That happens, by the way, in every family. My daughters tutor me, so it's not unusual. Okay, now let's look at the hydrogen. We have 18 hydrogens, and over here we only have 2. So I heard Jerry say 9. If I put a 9 here, that is indeed correct. If he weren't, remember, we're trying and then finding out if we're correct. So 9 times 2, 18. Now we have 18 hydrogens. That's balance for the hydrogen. So we're done with carbon, we're done with hydrogen. We have 2 oxygens, and we have 8 times 2, 16, plus 9 times 1, 9. We have 25 oxygens. An odd number. So how do we make this 25? Well, we can't, right? But what happens if I do the following? Divide that by 2, so 12.5. 12.5 here times 2 will make that 25. But unfortunately, we have to do the same for everything. Okay? So, if I put 12.5 there, it's going to balance it. 12.5 times 2, 25 oxygens, right? But I cannot use a 12.5. I need to multiply everything by 2. So I put a 2 here. 12.5 times 2, 25. 8 times 2 is 16. I'm multiplying everything by 2. 9 times 2 is 18. And now if we do the entire accounting again, I hope we are right. 2 times 8, 16 carbons, right? 16 times 1, 16 is balanced. Hydrogens, 2 times 18, oh my God, now 36? 36. Fix me if I'm wrong. 36 hydrogens. And 18 times 2, 36. So hydrogen is balanced. Now let's do the oxygen. 25 times 2, 50. And 16 times 2 is 32. Plus 18 times 1, 18. 18 plus 32, 50. We got it. And we got it by doing exactly what you guys did already, and that you know going forward is going to work. You divide by 2, you put it as a fraction, but then you multiply everything by 2 so that everything looks with whole numbers. Yes, sir?
Is the heat triangle required?
I don't think so in the answer.
Because I don't see where I can.
Right, I don't think so. So let's do toluene so that I show you. It is, there's an arrow with a triangle?
Arrows there, yeah.
Okay. So let's do toluene, and I'm going to enter that into the system so that you know how to enter it. It's not letting you.
When I put 50, it says wrong. You had to put the whole thing. So I put 50.
Yeah, so let me show you what we're going to do, John. We're going to do it with a different one. Well, actually, you know what?
Yeah, the whole formula.
I'm going to put it here for you, John. So this is not toluene, you guys. So bear with me. I'm going to put the one that we just did, octane, in here. So we're going to transfer this from here to the screen. And this is what I think you had to do. You had to put the entire chemical reaction. So you're going to put a 2. And then we have carbon. And it takes time, okay, because you had to use the templates here. So bear with us. For the 8, you click right here, John. And then you use the subscript, XB. This is subscript. And you put the 8. And then you had to click outside of that box, like that, to put the hydrogen. Now we put a capital H. It has to be capital, don't put lowercase. Click on the template for subscript again, put an 18, click out, and we're not done because we need to put this G. You need that too. So parentheses, G, close parentheses. Then we put the plus sign because we're combining that with oxygen. So plus, capital O for the, is 25 oxygens? Yes. So 25 first, oxygen next, that's not a 0, it's an O, and then the subscript 2. Click out, parentheses G for the gas. And then, as you guys were saying, there's an arrow here. And there may be an arrow with a triangle on top, but you don't need it. So there is an arrow, and now the products. So 16, CO2, carbon, oxygen, subscript 2, click out, parentheses G for gas, plus, finally the water. So you can't see it, but it's 18 waters. 18 H subscript 2 O, click out, capital O, and then parentheses G. And if I submit this, it's going to mark it wrong because this is for toluene. No, because this is for toluene, not for octane.
It is automatically going to assume that there's heat applied?
I think so. I don't think it's requiring you to put heat. So it is. You just put the arrow, right?
It says correct. Incorrect again.
Incorrect. Let's see. Let me get my glasses.
I'm sorry.
No, that's fine. It is a pain to enter.
Yeah.
So let me take a look.
Okay, thank you.
16 CO2. So what is wrong? Everything is right. Liquid. Oh, yes, that's. You know what? Excuse me, but I made a mistake. That should be an L because it says liquid.
Put a lowercase.
So instead of the lowercase g here, and only there, put a lowercase l. Not a number 1, but an L.
Okay, it's right now.
Yeah. So, my God, if you don't write it carefully enough, it did say liquid octane in your case. So you do have to put an L instead of a G. You're welcome. So for toluene, you just have to, of course, look at the formula. Let's balance it. If I enter this, it's going to be marked wrong. So let me just get out of here. Look for toluene's formula. We'll balance it, and with that, we will finish with what we needed to cover. So there is toluene. Toluene has a formula of C7H8. So let's change this. And let's balance it. It's the same thing. It's not an alkane, but it's going to be balanced the same way. So we have C7H8. Is that what I said? C7H8. You may be wondering, how on earth is that possible? This is L for liquid. Well, the formula of toluene looks like this. Shorthand. That's meant to be a hexagon. And you're going to go, what the heck is that? Well, at every corner here, you have a carbon. So this is carbon, 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 and carbon. 1, 2, 3, 4, 5, 6, 7, 7. And we have 8 hydrogens. So we have 1 hydrogen here. We have 1 hydrogen here. 1, 1, 1, 1, 1, 2, 3, 4, 5. And actually we have 2 here. No, 3 here. And that's toluene. Big deal. We still balance it the same way. So how many carbons? 7, right? And over here, only 1. So what do we do? 7. A 7 times 1, yes. 7 there. So now we have 7 and 7. How many hydrogens? 8. So 8 hydrogens. And over here we have 2 hydrogens. So how do we make this 8? 4 times 2. That's 4 hydrogens. Okay, so 7 carbons, 8 hydrogens, and that's balanced. Let me erase these. And now let's move on to the oxygen. 2 oxygens, and over here we have 7 times 2 is 14, plus 4 times 1 is 4, 18 oxygens. So it's not balanced. How do we make this 18? 9. 9 times 2 is 18. Yes. So now if we count, we have a balanced equation. 1 of these for 9 of that, for 7 of that, gives you 4 of that. And that would be liquid toluene. All right? And that's what you'll enter to get the right answer.